Welcome to Spring LIB.
All right, so the sun radiates at a rate of 4 times 10 to the 26 watts. And so this is talking about a power, and power is just energy over time. So when you're radiating a power of 4 times 10 to the 26 watts, that's 4 times 10 to the 26 joules that you're radiating per second. So that's energy, delta E over delta T, okay? And so that's how you relate power to energy. So the first problem wants to know the mass loss per second, as you have energy loss per second. And so from Einstein's famous equation, we have energy loss will be equal to mass loss times c squared equals mc squared. And so delta m is just delta E over c squared. And here we want the rate at which mass is being lost. So rate is just delta m over delta t. And so you basically divide the right-hand side here by delta t. So you have delta E over delta t times 1 over c squared. Delta E over delta t we have given. And so this is just 4 times 10 to the 26 joules per second times 1 over the speed of light squared. So that's 3 times 10 to the 8 meters per second squared. Note that joules is in terms of meters, seconds, and kilograms, so we're working in SI units, so we're fine. And so what you get here is that sun loses about 4.4 times 10 to the 9 kilograms per second. So about 4 billion kilograms every second. Yeah, that's insane, I know. Part B, wants you to know how long it would take the sun to lose a mass equivalent to the mass of the Earth. So from the book, or you can look this up, the mass of the Earth is about 5.98 or close to 6 times 10 to the 24 kilograms. Okay, and so very simply to work this out, we know that from part A that 4.4 times 10 to the 9 kilograms is lost in 1 second. And so 1 kilogram is lost in 1 over 4.4 times 10 to the 9 seconds. Therefore 5.98 times 10 to the 24 kilograms would be lost in 1 over 4.4 times 10 to the 9 times the mass 5.8 times 10 to the 24, which is equal to 1.36 times 10 to the 15 seconds. So, of course, what does that even mean, right? So we divide, so we convert seconds to years, and so we divide that by 3.16 times 10 to the 7 seconds per year. So that's how many seconds are in 1 year. It's a very handy number to know. Note that the seconds drop out, and what we end up with is something very close to 4.3 times 10 to the 7 years. Remember, 10 to the 6 is a million, so 10 to the 7 is 10 million. So this is about 43 million years that it takes for the sun to lose the Earth's mass equivalent to that of the Earth if it's radiating at that rate. Okay, and then part C asks how long the sun could last if it radiated at this rate. Okay, so delta P that we had in part A is constant. Okay, and so for this, basically you want delta T. So delta T will be, first of all, total mass of the sun over, and that should be divided by the rate at which mass is lost given its radiating at the rate mentioned here. So it would be this from part A, or sorry, this delta M over delta T from part A, right? And so mass of the sun, you can look this up or find from the book. It's 1.99 times 10 to the 30 kilograms. Yeah, I know, that's huge. And you divide that by your answer in part A, which is 4.4 times 10 to the 9 kilograms per second, okay? Yeah, so that gives you about 4.52 times 10 to the 20 seconds. And again, you divide that by 3.16 times 10 to the 7 seconds to convert that to years. And what you get is about 14 times, get this, 10 to the 13 years, or 14 trillion years. So the sun would last 14 trillion years if it shed its mass at the rate at which it is shedding right now, which from astronomy we know is not the case, but that is what you would get.